If you happen to watch episode 5, I concluded that episode by telling you that this episode 6 would be about electromagnetism. Guess what? I changed my mind and I decided that I needed me some strong nuclear force instead of electromagnetism. And we'll deal with electromagnetism in a later episode. So I know you probably think I'm a liar. You probably think that I can't be trusted, and you probably would be right, but I'm going to focus in on the strong nuclear force today. So let's get into it. So when you hear the word strong and nuclear and force together, does it sound powerful to you? I can tell you it does to me. And guess what? If you feel that way, you would be correct, because it is one of the most powerful forces in the universe. To give you sort of an analogy or to quantify it, the strong nuclear force is the number 1 followed by 38 zeros stronger than gravity. Now, we talked about gravity, and you think about, boy, that gravity seems to be pretty strong considering it's dealing with the planets and keeping them in order with the stars and moons and everything else. But if you write that number down and you look at that number, it's a number you can't even get your head around, that it's so massive in terms of the strength of the strong nuclear force. Now, the clue that it is strong ends up being, it rests with one of the words. You think it might be strong, you think it might be force, or is it nuclear? That's exactly right. Nuclear, when you hear the word nuclear, you are entering the world of the atom. And if you start mucking around with the atom, or the quantum world, the tiny, teeny world that makes up our universe, you're basically dealing with an immense amount of energy penned up in that atom. And if unleashed, it can do both good things and certainly not good things. So, for example, a good thing that comes from it is we generate electricity via nuclear power. Now, some people are for nuclear power, other people are against nuclear power, but what I can tell you is the end result is there is electricity generated from it. So we got that established. On the not so good side, we have thousands of nuclear warheads. And obviously, the negative is they're nasty beyond belief. On the positive side, they're a deterrent in terms of dealing with other nations. But anyway, I'm not going to get into any of that stuff. I'm just giving you examples where we as humans have leveraged that energy for certain needs that we have. Now, if you think about it, gravity is really this long-range type force. It's dealing with the planets and stars, etc., and it's keeping that in order. Where the strong nuclear force is dealing with the teeny world, and you go, wait a minute, it seems like it should be the complete opposite. In other words, we need the strong nuclear because we're with the force with the planets and stars because they're so big and massive, and gravity that could be good for totally different. It's just not that way. Nature is just doesn't work that way. At the atomic level, you need that level, that power, to keep things intact. Otherwise, things start going one of those numbers. Now, in terms of the atom, for those that aren't familiar with an atom, let me just give you a quick description of it. If you look online look online and look up atom, you'll probably see a drawing of a circle with one circle and then a smaller circle inside. And basically, they're going to be talking about there's protons and neutrons in the inner circle, small circle, that's the nucleus. And outside of that little circle, there's electrons. And basically, they're moving about, and that's generally about right. But in reality, an atom, there's really no boundary to an atom like the circle that they show, or even on the outside and the inside. It is more of an energy cloud, because on the outside, it's basically the electrons floating about with really no hard boundary, and the same thing with the nucleus. You have protons and neutrons in there, and they're doing their thing, all right? So it just, if you think about that atom, everything that we're aware of has atoms in it. I have atoms in me, you have atoms in you, trees, atmosphere, the pond behind me, the snow on the ground. Everything is an atom. And the strong nuclear force is working 24 hours a day to keep those atoms intact. So you sort of get the feel for that. Now, in terms of the strong nuclear force, what I'm going to talk about in this episode are 4 particles that are in the nucleus. I only mentioned 2 of them. I mentioned the protons and neutrons, but there are 2 other particles that I want to mention too, and they are quarks and gluons. So there's 4 particles that I'll talk about today that reside in the nucleus, with electrons being outside of the nucleus, which I'm not going to talk about today because the strong nuclear force is really separate from that part of the atom. So we'll keep it to the nucleus. Now, to give you an example of the number of atoms that are out there, we'll use the human body as just that example. There are 7 octillion atoms in a human body. So once again, octillion, what's that? That's 7 followed by 27 zeros. That's a lot of atoms just in me alone. And you multiply that by all the people on Earth, and you got yourself how many atoms really that are walking the Earth right now. Now, on top of that, like the trees all around me, they have atoms in them too, and they have a different count in terms of their atom count. And the snow on the ground. And it becomes a number that's just so massive, once again, you can't even get your head around it. But the fact of the matter is, the strong nuclear force is involved with every atom, whether it's me, you, the snow, whatever, 24 hours a day, making sure that that atom maintains its integrity. So that's the foundation of basically what an atom is. So in the episode, the rest of the episode, let me get into the 4 particles inside the nucleus to give you a better understanding of what those are and how they play into the strong nuclear force, how that all sort of plays together. So let's start off with a quark. So our quark is a fundamental particle, and a fundamental particle is one that it's not made up of any other parts. In other words, there's not a little bit of this and a little bit of that to make up the quark. The quark is the quark. And what quarks do is they are used to form protons and neutrons in the nucleus. We'll get to that here shortly. You can think of quarks as the bricks of what makes up protons and neutrons. And you look at that and you go, okay, well, how are they held together? I'll get to that shortly. Now, as with everything else in the universe, it seems like everything's invisible, and quarks are no different. The quarks you can't see them, but guess what? They have a weight, a mass to them. They have a charge to them, and they spin. So basically, you can't see it, but it's there doing its thing. And on top of that, there are 6 flavors or types of quarks. And in this episode, I'm only going to be talking about the up and down quarks. The 4 other types are top and bottom, and what is the name of the other 2? Charm, and the other one is strange. And strange is a weird name because to me, all of the quarks are strange. So go figure. So now you got it. We have protons and neutrons. They're made up of quarks. Okay, got that. Now, let's talk about these quarks a little bit more in terms of their personality. Quarks, they do not like being alone. So what they constantly do is they hang out with one another. And when they hang out with one another, what ends up happening is when 3 of certain types or flavors of quarks get together, they form a proton. And if 3 other configurations of quarks get together, they form a neutron. Boy, that's pretty amazing. So the idea is if 2 up quarks and one down quark get together, they form a proton. If one up and two down get together, they form a neutron. There you have it. That's how it's formed. So the way nature is, of course, nature's always trying to break things down. So the quarks are well aware of this. And what they do is they keep close by these guys called gluons. They're also particles, fundamental particles. And as I mentioned before, these gluons, they're sort of like glue. Not only that, they bond those quarks together. They are the mortar to the bricks that the quarks are, and it provides stability to both the protons and neutrons. And as a result of those gluons, it basically, because of that bonding, that's what the strong nuclear force is all about. That it's created, and it's basically the gluons are carriers for the strong nuclear force, and that's what binds everything together, and it's the reason why it's so strong. So you have these invisible tiny particles that are creating this energy that is just so immense that the extremes are, once again, it's weird to think about it, how something so small could create so much energy, so much power behind it, but that's what it is. And one final thing about gluons, just so you know, there's 8 different types of gluons. So you have these combinations of 8 gluons and 6 quarks, and there's just it's a crazy party going on inside of an atom for sure. Now you sort of have an idea of what forms the strong nuclear force, which is basically the gluon holding the quarks together so they can create protons and neutrons. Now, why do you need protons and neutrons, and what are these protons and neutrons? So let's look at protons. Protons are subatomic particles, which means they're made up of other particles. And just as we learned, they are made up of quarks and gluons. So there you have it. Now, on top of that, protons have a positive charge. Now, you've heard of charges before. There's electrons, you may have heard, have a negative charge. Protons have a positive charge. And what that means is, a good example of that is if you have magnets, 2 magnets, and you put the 2 positive sides together, they repel from one another. If you put the 2 negative sides together, they repel from one another. But if you put the positive and the negative next to each other, they come together. They just love each other like crazy. So in terms of a proton, it has a positive charge, which means when you're around it, if you're holding those magnets, it's an outward force that you feel in the air around the magnets. If it's a negative charge, it's a pulling sensation force of that air around you. And so if you think about it, if you have 2 positive ends of the magnets coming together and they're pushing, you can't get them together because each force is pushing against each other. And the same thing happens with electrons. If you have the 2 negatives together, they just don't want to be together. So the positive and negative, they definitely go hand in hand. Well, that's a good thing, except for it can cause a problem at times also. So if you think about a proton, it's in the nucleus, and there's electrons going all around it. And if you think about it, the protons and the electrons really are attracted to one another. So there has to be some delicate balance of how do you keep them separate, because like magnets, they want to be drawn toward each other. So it has to be this game where we don't want the electrons to fly out of the atom, but yet we don't want them to get too close to the protons, because they'll go into the nucleus to be with them, because opposites attract. So it's that dance, the dance that goes on between those two, and that's where the strong nuclear force comes in, and also there's the electromagnetic force with the electrons, which again is another episode. So you see that it's a crazy place within these tiny atoms, and it's happening all the time. It's nuts. Now, what's weird about a proton is a proton, even though it has a positive charge, and an electron has a negative charge, their charges are equal in terms of their strength, even though they're opposite. But what's weird about it is a proton is 1,836 times heavier than an electron. So you go, wow, that's really weird. It's massive in terms of its weight compared to an electron, but in terms of its charge, it's equal to this little electron. So either that electron is really jacked up, or that proton is really weak and needs to hit that gym for some resistance training or something, because it's not really that strong relative to its size. But different story. So now you have an idea what the protons are. Now the neutrons, they also are subatomic particles made up of quarks and gluons. And what they are, they have a neutral charge. They're not really attracted to either protons or electrons. And what they do is they act like a referee. They're mediating. In other words, they're saying, okay, protons, we're in this nucleus together, and because protons, when you put them together, two positive charges, they want to separate. So he steps in and says, look, you guys, enough's enough. Quit doing this, because if you come together or you separate too much, you might leave the nucleus, and our atom will not be the same. It will cease to exist without you. So settle down, stay in here, and quit repelling each other to the point of compromising the nucleus. On the other hand, there's the electron out there, and it's trying to draw it's luring those protons out there, because it has that negative charge, and that negative and positive charge, they just want to be together. So the electron's being drawn in, the proton being drawn out by the electron also fighting with the other protons. So you see this crazy thing, the dynamic environment. It's chaotic, but yet controlled. And one of the reasons why it's controlled is because of the strong nuclear force, because how it deals with the quarks and gluons to deal with that dynamic environment, and it plays a very important role in that. So hopefully you understand that. Now, back to the atom again, and which we talked about a little bit about. Now, as I mentioned, the atom is the building block of all matter. And matter basically is we're talking about, when we talk about matter, we're talking about the elements. There are 118 elements in our periodic table. And if you're not familiar with the periodic table, you're in luck, because I'm going to create another episode on the periodic table. But basically, the elements of the periodic table are things you've heard about before. For example, you've heard about carbon, you've heard of hydrogen, oxygen, silver, gold, for example. Those are all elements. And each of these elements, they have their own distinctive atom. So atoms are different because there's a different number of protons in them, and neutrons in them, and electrons in them. And that variation in the number of protons, neutrons, and electrons give them their particular behavior, because each of these elements, they bring something to bear. They're different from one another, just because of just slight changes in, just say, the number of electrons or protons, etc. Get the picture. So let me give you an idea of how small atoms really are. Now, I gave you a number in terms of the number of atoms in the human body, but let me give you an idea of how many gold atoms are in an ounce of gold. So an ounce of gold is basically, you can think of it maybe 2 inches tall, a little over an inch wide, and half an inch thick. In that little piece of gold, there are 8 followed by 22 gold atoms in that. So you think about it, and they're all, as I mentioned, atoms are this basically this energy cloud, and they're all squished together very tightly into that gold piece, in terms of just really in there, really tight, that 1 ounce of gold. So it just goes to show you there's a lot of atoms, again, on this earth. And as a matter of fact, that number that I just gave you in terms of 8 followed by 22 0 gold atoms in an ounce of gold, comparatively speaking, if you compare it to the number Google. Now, for those of you that are familiar with Google, I'm not talking about the search engine, and I'm not talking about, their website, the company. I'm talking about the number Google, which, by the way, that's where the Google name came from. And Google is a number, and by the way, it's spelled Googol. It has 1 followed by 100 zeros. That's what a Google is. So relative to 1 Google, this 8 followed by 22 zeros is like, well, that's like nothing. But the bottom line is 8 followed by 22 zeros is a lot of atoms. And you think about in context of everything around us. Who knows how many atoms are out there? It's just so insane. So there you have it. You have the strong nuclear force is keeping the atom intact by making sure that the gluons are there to support the quarks, and the quarks are there to support the protons and neutrons, and they're there to keep stability to the nucleus, to keep interacting with the electrons on the outside, so that the atom maintains its integrity, so it doesn't cease to exist, and life continues, and you get the picture. So it's a very important force that holds basically everything that we know of together and keeps us on this earth. And there you have it. So in the next episode, assuming you believe me, considering I lied the last time, I'm going to be talking about the weak nuclear force. And the weak nuclear force, it'll be described in context of our sun, and or for that matter, any sun. So with that said, I'm signing off, and I'll talk to you in the next episode. Have a good one.